Okay, the first problem on the study guide for test 2, the graph of f is given, find each limit. So if you recall, for limits it says x is approaching -3 from the left. So if I consider 1, 2, 3, -3 here, and we're approaching from the left, anytime you're doing a limit, you're on the graph itself. Your graph is approaching the x-coordinate that they care about, and your question is asking you where is the y-coordinate going to. So at -3, coming from the left-hand side, we're getting close to the y value of 2. If we consider also -3 from the right-hand side, still doing a limit, so we're still on the graph. We're going towards the x value of -3 from the right-hand side. And we can see here that this is approaching 1, 2, 3, 4 negative, so that's the answer to that. As far as the limit as x approaches 4 from the left, now we're 1, 2, 3, 4, we're right here at this vertical asymptote. From the left-hand side, again, we're doing a limit, which tells me I'm on the graph. I'm riding along the graph approaching from the left, so I'm going this direction. The graph seems to be going straight up. That tells me positive infinity is the limit. As we approach 4 from the right, again on the graph, there's x equals 4. I'm approaching 4 from the right. The graph seems to be going straight down, which gives me a value of -infinity. For the limit as x approaches 4, not from the left or the right, but just as it approaches 4 in general, the left and right hand limits are going different directions, which tells me the limit itself does not exist at 4. The only way a limit can exist is if its left hand and right hand limits are equal to each other. For part F, the equations of the vertical asymptotes, I can clearly see there's one here at 4, and there's another one here at 6. 4 and 6 are the numerical values where they occur. They're crossing the x-axis, they're vertical lines, so we write vertical line equations. So x equals 4 is the equation of one vertical asymptote. X equals 6 is the equation of the other. If you leave the x equals off, you're not right. If you write x equals 4, 6, something along those lines, you're going to lose credit because you're being a little bit lazy. So, a different equation for each one. Don't give me this type of answer when you have multiple asymptotes. One other thing they might ask you on a question like this, suppose they ask for f of a number, f of -3 for example. If they're asking f of -3, they're asking where's the dot. So at -3, there's a closed circle right here. At +2, so that equals 2. If they were both open, then the answer would be does not exist. It doesn't ask for one here on the study guide, but we've had dealt with this stuff in class, so I wouldn't be shy about putting something like that on the test. Practice 2 or example 2, sketch the graph of a function f that satisfies all the following conditions. My advice on these was to put open circles for each limit. So at -2, I'm going to put a point at 3. So -2, 1, 2, 3, open circle. The next limit I'm looking at, -2, goes to 4. So -2, 1, 2, 3, 4. There is a from the right, from the left. We'll worry about that when we start actually drawing the picture. F of -2 equals 1. This gets back to the point I was just making a moment ago. F of -2 is a closed circle. So x equals -2, y equals 1. There's a closed circle here. It doesn't necessarily have to hit in one of the limit values when we're graphing these or when we're drawing a graph. Next thing I see, f of x approaches, limit of f of x approaches 3, or limits -infinity. And if it's approaching negative or positive infinity, that tells me there's a vertical asymptote. So at 3, I'm going to put a dotted line to represent a vertical asymptote. Coming from the left and from the right, I got a -infinity, positive infinity. Either one of those is going to create the asymptote. So I've got this for my picture so far with limits. At this point, I start connecting the dots, or at least I'm drawing the graph. We always start at -infinity on x. We're going to end at positive infinity on x. And we need to go from -infinity to a point, and each point to each next point, or asymptote. So as x approaches 2 from the left, okay, from the left is what we're concerned with here. I'm supposed to go to 4. So I've got 3 dots actually I could go to, but I'm coming from the left, I'm going to go to the dot 4. So that if I were trying to determine the limit from the left, the limit's approaching a height of 4. From the right it's approaching a height of 3, so I continue on my graph here, this way. Now as far as where I go up or down, I got to look at my next limit, so the next spot anything happens here is the vertical asymptote. As we're approaching 3 from the left, it's supposed to go to negative infinity, so if I'm coming from the left-hand side, make my graph go down to negative infinity. As I approach x equals 3 from the right-hand side, it's going to positive infinity, so the next place would be going straight up there, and then as it goes off to infinity, it goes off like so. That is a graph that works. It doesn't have to look exactly like that. Whatever it's doing in the spots where it doesn't say anything about limit, you can be creative, just don't go backwards. So if I'm going here, I could do something like this, and maybe I can do this here, and maybe something weird like this here. That red graph represents the same thing as blue graph as far as the limits and the function of values are concerned. As I'm approaching from the left, it's hitting a height of 4. As I'm approaching from the right, it hits a height of 3. As I approach from the left at 3, it's going to negative infinity. From the right, it's going to positive infinity. It has a point at 2, negative 2, 1. Both those graphs are fine. I'd do the pretty simple one myself if I were doing a test, but you guys can get creative there. Just again, don't do something weird like this where it kind of comes up and then goes back around and does something weird like that. Now it's not a function anymore, so vertical line test would fail on that. So make sure it says a function f. Make sure that it doesn't go backwards when you're drawing it. If you want to get creative in how it looks, that's fine. I would personally have probably something like the blue graph if I did it. Next thing, example 3. Find the limit 3 plus h squared minus 9 over h as h approaches 0. This is just a straight simplification problem. If I simplify that as much as possible, starting with 3 plus h, the quantity squared, that's just a binomial squared. So I'm going to continue to get limit as h approaches 0. I'm going to leave the minus 9 and the over h alone. And if I just worry about this 3 plus h squared, that's going to be 9 plus 6h plus h squared. Squaring binomial is what it always has been. We square the first object, we double the product of the two, we square the second object. What happens next in simplifying, my problem is the h equals 0 on the bottom. If I try and substitute h in immediately, I can't do that. So 9 minus 9 cancels, because it does. At this point, every term contains the letter h, so reduction by h is legal. So limit as h is approaching 0. If I take an h out of every term that's got an h, I'm going to get 6 plus h over 1. The over 1 is not necessary to write. And once I get to a point where there's not division by h, substituting h equals 0 when it's legal, 6 plus 0 equals 6, and that's my answer. So expect a similar structure on the test. I might even go cubic on this, but if you cube it correctly, you should get the same number as that number. They cancel, everything else has an h, you cancel it out. I might stick to squared, I don't know, we'll see. But we've dealt with cubes on binomials, so I wouldn't feel bad about that. Number 4, find the limit as x approaches 4 of this thing. Now, what I should have done in the last problem, I didn't do. Let me go back to real quick. If I just try and put h in immediately, 0, 3 squared is 9, 9 minus 9 is 0, 0 on the bottom. Get my indeterminate form to see that maybe there's some algebra that I can do to get the answer. The reason you want to always put the number in first, if you take a look at this problem, if I substitute x equals 4 in for all the x's, on the top I'm going to get x squared, which is 16. Again, I'm replacing x with 4. Minus 3 times 4 is going to be minus 12 plus 2. On the bottom, we get x squared, which is 16, minus x, which is minus 4 minus 2. That ends up getting me 6 on top, and 16 minus 6 is 10 on the bottom. That equals 3/5, and I'm done. So there'll be one problem on the test, one limit problem at least, where all you have to do is put the number in. I'm not necessarily saying it's number 4, but it'll be in that limit section where they're all evaluate the limit or find the limit. Try putting the number in each time. One of them will just be simple arithmetic. So get yourself an easy 8 points on a calculus test there. Number 5, same deal here. If I try to stick 2 in for x, I'm going to get 2 squared is 4, 3 times 2 is 6, minus 10 on top. 2 squared is 4, plus 2 times 10 is 20, minus 24 on the bottom. 10 minus 10 on top is 0. 24 minus 24 on the bottom is 0. I get an indeterminate form, which means I need to rely on algebra now. Notice this time that we have quadratic trinomials, so we're looking to factor those quadratic trinomials. That's the typical technique we're going to do if we get 0 over 0 in this scenario. X plus 5 times x minus 2. 5 and negative 2 multiply to make 10. 5 and negative 2 add to make positive 3, since we have a coefficient of 1 in front of the x squared. On the bottom, x squared plus 10x minus 24. It'd be x minus 2x plus 10. Oh, that's not right. X plus 12. That's better. All right. Negative 2 times 12 is negative 24. Negative 2 plus 12 is positive 10, so that's correct. And we're still doing a limit as x approaches 2. And you'll notice that x is approaching 2. X minus 2 equals 0 when x approaches 2. This x minus 2 also equals 0, so that's what's creating our 0 over 0 indeterminate form. But since we have the same expression on top and bottom, we were able to cancel those out. That gets rid of our problem. What's left is just a simple x plus 5 over x plus 12. I'm going to change all the x's into 2's. Since I've gotten rid of the division by 0. That gives me 2 plus 5 on top, 2 plus 12 on the bottom, for a total of 7/14, better known as a half. So your goal for these limits is get to a point where you can put the number in for the x's or the h's, whatever letter is there, by getting rid of the division by 0. Number 6, find the limit. And now this time, if I try to put 3 in, I'm going to get 12 on top, I'm going to get 0 squared on bottom. Now this is not an indeterminate form, this is an undefined. So if I get indeterminate, I'm expecting to get an answer like a half or 3/5, or actually not even 3/5, that wasn't even indeterminate, but 6, 1/2, stuff like that. When I get indeterminate, I'm looking for algebra to do something like this to get rid of my division by 0. When I get undefined, I can't get rid of my division by 0. There's no x minus 3 on top to cancel the x minus 3 on the bottom, creating the 0. So when you look at this and you see undefined, you're expecting an asymptote, and your limit's either going to be going to positive or negative infinity if it goes to either one. If it goes to the same one, it's positive infinity. Same one down, negative infinity. If it goes to opposite, it does not exist, because this is x is approaching 3, not from the left to the right. So what I want to do is I want to use a chart, my calculator ready to go. I'm going to let this function be called f of x, just to give it a name. And I'm going to let x approach 3 from the left, to determine what infinity it seems to be going to. And I'm going to approach it from the right also, 3.001, 3.01, 3.1. So this is approaching from the right, starting too big and getting smaller, starting from left, starting too small, getting bigger. Both cases getting closer and closer and closer to the value of 3. I want to evaluate f of x, which is the function at each of those values. So if I go back to my calculator here, type in 12 on top divided by parentheses x minus 3 in parentheses squared. Go to my chart, my table, and I just type in the numbers that I've determined to use, which are numbers really, really close to 3. 2.9, that's 1200. 2.99 comes out to 120,000. 2.999 comes out to 1.2 E7. Also known as 12 million. Alright, so I've got 1,200, 120,000, and 12 million. Okay, so as I'm getting really, really close to 3 from the left-hand side, the numbers are increasing rapidly. That tells me I'm getting towards a value of infinity. The reason I chose these specific numbers here is because x is approaching 3. If x were approaching 7, I would have gone 6.9, 6.99, and so on. So be careful you pick the correct numbers based on what x is approaching. If I pick my other numbers, 3.001, 3.01, and 3.1, we're getting the same results. So this 3.1 is the furthest away from 1200. Getting a little closer, I get 120,000. Getting a little closer, I get 12 million. So as I'm approaching from the right-hand side, my outcomes are also increasing without bound. So both sides, the left-hand side is going straight up, the right-hand side is going straight up. They're both going to the same infinity, so infinity is the solution. If these infinities didn't match, we'd put it does not exist. If they were both negative infinities, negative infinity would be the right answer. So again, if you get an undefined, chart's the only way to do it, and it's up to you to determine whether they're approaching a positive or negative value. Again, they're going to grow rapidly like this. If they're all positive, it's positive infinity. If they're all negative, you get negative infinity. Number 7, I'm trying to put 9 in for x. I'm going to get 3 minus the square root of 9 over 9 minus 9. Square root of 9 is 3. 3 minus 3 is 0 on top. 9 minus 9 is 0 on the bottom. We get indeterminate form again. This has a radical structure to it. So usually what we do in a situation like this is I take my limit and my expression that I have over here, and the easiest way without having to think too hard is to multiply by a conjugate. So if I rationalize the numerator, so that's going to be 3 plus the square root of x on top and 3 plus the square root of x on the bottom. Be cautious that 9 minus x is treated as one object, so we're multiplying this entire object, 9 minus x, times this entire object, 3 plus the square root of x. 9 minus x is the issue because that's creating the division by 0. 3 plus 3, which is the square root of 9, makes 6, doesn't make 0, so multiplying that's not going to create extra problems. If I do my stuff on top, multiplying conjugates, I just get first times first, which is 9. Outside 3 square root of x, inside negative 3 square root of x cancel. Last times last, negative times positive makes a negative, square root times itself makes the inside of the square root, so x. On the bottom I got my 9 minus x being multiplied by my 3 plus the square root of x. Still doing a limit as x approaches 9. Okay. Keep the object that's causing the problem segregated from everything else. Don't multiply it out. It is counterproductive to do that. So keep that separated because that's what we want to get rid of. And ideally this type of thing happens. A 9 minus x on top and bottom, cancel. Everything off the top means a 1's left on top. 3 plus the square root of x ended up on the bottom. At this point, if I substitute x equals 9 and I get 1 over 3 plus the square root of 9, 3 plus 3 is equal to 6, so 1/6 would be the value of the limit. With all these limit problems, a numerical chart like that is legal to use. If there's a possible exact answer like 1/6, use a chart, give me a decimal approximation. You lose a little bit of credit for that, maybe a point or two for not going through the algebraic technique, but 6 points is better than no points. So make sure that you realize that chart technique is a fallback method if you completely space off how to do this kind of stuff. Number 8, another limit. Notice on top we have x squared, which would be 9 since x is approaching 3, plus 12 times 3 is 36, minus 45. On the bottom I get 3 to the 4th, which is 81 minus 81. 45 minus 45 is 0 on top. 81 minus 81 is 0 on the bottom. Once again, an indeterminate form. The top is a quadratic trinomial, just like those other quadratic trinomials, so we're looking to factor that in that manner. In order to get a negative 45, I have to have a positive and a negative. Looking for a positive 12, so I'm going to go with 15, positive, 3, negative. Negative 45 product, positive 12 sums. That would be the correct factor form for the top. The bottom is x to the 4th minus 81, which is a difference of squares because they're both perfect squares. Even powers, and 81, of course, is 9 times 9. So I can factor that out to x squared plus 9 times x squared minus 9. X is still approaching 3. If you're not sure what to do at this point, try putting 3 into both of these factors at the bottom. 9 plus 9 is 18, not 0. 9 minus 9 is 0. So my 0 is living in this thing, but I can't cancel because it doesn't match anything up there. But this is fine because it doesn't make 0. So I'm looking to factor this a second time. And if hopefully you'll notice x squared minus 9 is another difference of squares. So everything else stays the same. I'll do this in black. So limit as x approaches 3. The top is staying x minus 3 times x plus 15. This term here, x squared minus 9, is staying the same. But then x squared minus 9 is going to factor as a difference of squares. The square root of x squared is x, square root of 9 is 3. We do square roots as a sum and a difference. And notice now this cancels with that. And we're left with x plus 15. If the top equals 0, I don't care. But 3 plus 15 equals 18. 3 squared, 9 plus 9 is 18. 3 plus 3 is 6. So there's no more zeros in this problem. So at this point, if I substitute 3 in, 3 plus 15 on top, 9 plus 9 times 3 plus 3. That gets me 18 over 18 times 6. 18 times 6 equals 180 if you care, but notice the 18s cancel. That is coincidental, doesn't always happen. If it didn't cancel, then you can always just multiply the stuff together, but a lot of times these things reduce, so look to do that possibly. I am looking for the reduced fraction answer for that problem, which it should have one. Once again, let's say that you completely space off how to factor difference of squares. You're not even sure how to get to this point, then you wouldn't even recognize it happening again. Again, fall back to that table, give me an approximate answer, get 6 out of 8 points probably. Again, I'm thinking I'll probably deduct a couple points for that because, I mean, this is Algebra 1 material here, so I would expect everybody to be able to master that by now. So if you haven't, you're going to lose some points, but it's better to get some than none. Number 9, use the intermediate value theorem to show there's a root of the equation that on the interval 0, 1. They've already given me the equation in the proper form to use the intermediate value theorem at equals 0. So step 1 is I'm going to say the domain is all real numbers and 0, 1 is a subset of all real numbers. Always start off with a statement of domain for the function you're going to deal with. This is a polynomial function, cubing, squaring, multiplying by 5, multiplying by 2, multiplying by 3, adding and subtracting. There's no limitations for x's in that situation. I can take any number to a power, any number times another number, any number added to another number. So there's no restrictions on this function. Domain's all real numbers. Every interval is a subset of all real numbers. The problem on the test will have a domain and the interval will be a subset of it. So this will be there, but just you need to make the statement in order to apply the theorem. Step 2, we want to establish what type of function it is. I'm going to also name the function. Let f of x equal 3x cubed minus 2x squared plus 5x minus 2. Whatever equals 0, let f of x be that thing, or g of x, whatever you want to call it. Just give it a name so you don't have to keep referring to that polynomial. You just call it f of x. And then I'm going to state that f of x is a polynomial function. As far as what we covered in this class, intermediate value theorem was good for polynomial functions, trigonometric functions, radical functions, rational functions. It will be one of those 4 types or a combination. So if it said 3x cubed plus sine of x plus the square root of x plus 1 over x, it would be all 4. Okay? The domain wouldn't be all real numbers in that scenario, but you know, it'll be whatever it is. But just know that whatever type of function each term is has to be accounted for. So if sine of x shows up, that goes in a trigonometric function. If the square root of something shows up, that's a radical function. If something over x shows up, that's a rational function. So name them for what they are. Any term containing any one of those types of things has to be accounted for and has to be named. Step 3. Once I've established I've got a subset, 0, 1 is a subset, and I've also established that f of x is a polynomial function, which makes it continuous on its domain. I'll write that statement. So f of x is continuous on its domain. So we've established that 0, 1 is in the domain, and our function f of x being a polynomial function is continuous on its domain. So now we go on to establish its value. So I'm going to do f of 0 equals something, f of 1 equals something. All I got to do to evaluate f of 0 is change all the x's into zeros. So I'm going to get 3 times 0 minus 2 times 0 plus 5 times 0 minus 2. So f of 0 equals -2, a negative result. F of 1 would be 3 times 1, which is 3, minus 2 times 1, which is 2, plus 5 times 1, which is 5, minus 2. 3 plus 5 is 8, minus 2 is 4. Okay, so f of 0 is -2, so imagine if we were graphing 0, -2, and I've got 1, +4. My graph is continuous. I got a dot here and a dot here, and I got to connect the dots. There's no way to connect those dots without crossing the x-axis, which establishes that there has to be a root. So that's this whole idea of the intermediate value theorem is that you show a negative, you show a positive, show there's no break. There's no way to connect the dots without crossing the axis. So therefore, you have a root. So once you've established all three things, 1, 2, and 3, we can go on to state that by IVT, f of x has at least one root on the interval from 0 to 1. Okay. It might have multiple roots. Maybe it does something like this. Maybe it goes up and down like that. It has 1, 2, 3, 4, 5. I don't know. It might have 5. We say at least because we know there's at least one. There might be more than one, but the theorem proves for a fact there's at least one. It doesn't guarantee there's any more than that or any less than. It could be exactly one, could be more than one, but you say at least one. Number 10, same idea. This one does have a trig function in it, so it kind of hits that other technique, that other thing I was talking about. So first off, it doesn't say equals 0, so the first thing I would do is I'd move everything to one side. I'd probably move the 2 and the -3x over to the left. It doesn't matter which one you go with. It just, the only difference is if you move it one way than the other, you might have negatives where other people have positives, but the sign change should still occur. So if I do 3 sine of x minus 2 plus 3x equals 0. So start off with that. Be careful if you're going to use a calculator to evaluate that you put it in parentheses around that to ensure that you're just doing sine of x, not sine of x minus all that other stuff. Looking at it, it's a sine function, which is all real numbers. It's a polynomial function, which is all real numbers. So as far as domain is concerned, it's still all real numbers. So my first statement is going to be the same. The domain is all real numbers, and 0, 1 is a subset of all real numbers. So that's statement 1. State the domain and state that your interval itself that you're working with. Here's my interval again. Notice the last problem was 0, 1. If that said 5, 6, we'd put 5, 6 here. All right, 0, 1 is a subset of all real numbers. Step 2, we want to name the function. Let f of x equal what we have as our function, so 3 sine of x minus 2 plus 3x. And I'm going to say that f of x is a trigonometric because of sine of x and polynomial because of -2 plus 3x. Function and is continuous on its domain. You have to state that. It is a necessary statement in order to use an intermediate value theorem. Intermediate value theorem requires that the interval you're dealing with is a subset of the domain and that the function is continuous on its domain. That shows the continuity. There's no breaks in the graph because of statements 1 and 2. Statement 3, I want to evaluate the function at 0 and 1, my endpoint. So I'm going to do f of 0 equals and f of 1 equals. For 0, that's easy enough. Sine of 0 is 0, so 3 times 0 is 0, minus 2 plus 3 times 0 gets me -2. 1 isn't quite as easy because, I don't know the sign of 1 off the top of my head. Make sure if you're evaluating radians that you are in, evaluating trigonometric functions, make sure you're in radians mode. If I push the right button here, radian mode, okay? And I'm going to just type in, for 1, it's going to be 3 sine 1. And again, sine, beginning parentheses, end parentheses, I just want to take sine of x, x equals 1, minus 2 plus 3 times 1 equals. That comes out to 3.5244. If you wanted to write 3 sine of 1 minus 2 plus 3 times 1, whatever here equals that, that's fine. If you're using a calculator to evaluate, I'll just believe you typed in your calculator. Hopefully you do it correctly. Notice I got a negative result, I got a positive result. Same thing happened. So I'm at 0, negative 2, I jump up to 1, 3.5 something. It's got to cross the x-axis, so that's the final step here to state that by the intermediate value theorem, f of x has at least one root on the interval from 0 to 1. Smartest thing I would do if I was preparing for this is I would get comfortable with what each step does. The wording isn't as important to me as that you do what you're supposed to do. State the domain and that your interval is part of the domain. State the function's name and tell me what kind of function it is, and state it is continuous on its domain. State that. Evaluate the function at the two numbers. Ideally the signs change. If they didn't change, let's say this f of 0 is equal to 1 and f of 1 is equal to 3.5244, then try f of 0.1, 0.2, 0.3 till you get a negative. All right? You're going to get a positive or negative on one of them. If you don't get the opposite sign, just move inward. So if 0 is here and 1 is here, and they're both positive, something along there has to be negative because they wouldn't have given you a problem that doesn't work. So if you eventually find, let's say at 0.5 it ends up being negative, it's going to get one root. It's actually going to get a second root at least, but we can still just say it has at least one root. So that's what your last statement. By IVT, f of x has at least one root on whatever the interval is. So kind of know what each part's supposed to do. Put it in your own words, but make sure what's supposed to be stated is stated. And again, make sure you mention all types of functions that it is. If you just say polynomial, leave off the trig, you're going to lose a point or two. If you don't state the continuous on its domain, you'll lose a point or two. So that kind of thing is going to happen. Number 11. Find the slope of the tangent line to the curve y equals 5 minus 3x squared at the point 1, 2, and find an equation of the tangent line at 1, 2. So, to find the slope of the tangent line, this is coming off of chapter 2.6, and we can also use our techniques from 3.2, since we've been dealing with that here for the last couple days. We're going to do the definition of a derivative to find the slope formula for that function. So, I'm going to do f of x is the function, 5 minus 3x squared. F of x plus h is going to be 5 minus 3 parentheses x plus h squared. And if I simplify f of x plus h, 5 minus 3 parentheses x squared plus 2xh plus h squared. If I distribute the negative 3 through, it's going to be minus 3x squared. It's going to be minus 6xh. It's going to be minus 3h squared. I'm going to caution some of you, I was grading homework on 3.2. A lot of you are not distributing. You're getting this negative 3x squared, but then you say plus 2x plus h squared. This x plus h squared is in parentheses. The 3 is being distributed through. The minus sign is also. And that's another thing I noticed a couple of you didn't distribute that minus sign through. So be cautious. Your algebra is good in the technique. Our derivative formula, f prime of x, is the limit as h approaches 0 of f of x plus h, which is all this stuff, 5 minus 3x squared minus 6xh minus 3h squared. That's f of x plus h. We're subtracting from it f of x, which is 5 minus 3x squared. And all of it's over h. F of x plus h minus f of x over h, that's the magical formula that's going to get us a derivative every time. What I told you should happen, if you're doing it correctly, I'm going to distribute a minus sign through this parentheses. 5, this 5 minus that 5 cancels. This negative 3x squared minus this negative 3x squared minus minus makes plus cancels. Everything that is f of x should cancel. Everything that is f of x plus h should have pieces of f of x in it, plus some h stuff that's extra. So all the stuff that doesn't contain h should match f of x. They should cancel out. The remaining pieces are negative 6xh minus 3h squared all over h. At this point, everything has an h on it, so canceling by h is legal. So limit as h approaches 0 of negative 6x minus 3h. H cancels. One of the two h's cancel, leaving me an h left over. And if I substitute in 0 at this point, negative 6x for h plus 0 gets me negative 6x. Okay, so all that work was to get me a slope formula. Okay, so all that work gets me this information. That my first derivative, f prime of x, is equal to negative 6x. So to do step A, once I've got my slope formula, it's real simple. Step A, find the slope at the point 1, 2. That's x equals 1, y equals 2. My slope formula has an x in it. So f prime of 1 is going to equal the slope, which is going to be negative 6 times 1. Okay, so that's how you're going to find slope on this. Other techniques you could do to find the slope of that would be to pick values very, very, very close to x. Do y minus y over x minus x, and let x get really, really, really close to 1, and then see what the limit's approaching. This is much more efficient. Got to do a little bit of work here, but the work's all algebra, and it gets you a nice little formula. Whatever x is goes right there, and you work it out. There's your slope. So that's how I do part A. Once I've found my derivative, I just apply the slope formula. For part B, find the equation of the tangent line at 1, 2. This is just algebra 1 again. I've got a slope, I've got a point, and I'm trying to find the equation of a line. Y equals mx plus b is my structure. Y is 2, x is 1, and m is negative 6. So y is 2, m negative 6, x 1. So 2 equals negative 6 plus b, so b is equal to 8. So y equals negative 6x plus 8 will be the equation of the tangent line. These problems are very easily checked. If I graph both y equals 3x, or 5 minus 3x squared, and y equals negative 6x plus 8. As far as the window is concerned, 1, 2 is my point of tangency, so I want to make sure 1, 2 shows up. Maybe negative 3 to 6. 1's between negative 3 and 6. And maybe negative 2 to 8. 2's between negative 2 and 8. Hit graph. I should get a parabola, and I should get a line that looks very tangent, hopefully. There he goes. Looks very tangent there, so it shows me that I'm probably correct with my answer. Number 12. The displacement in meters of an object moving in a straight line is given by this equation, where t is measured in seconds. Find the average velocity over the following time periods. Okay, so what I told you to do on this is to evaluate this function here without rounding for these t values. So I'm going to try 1, 1.1, 1.01, 1.001, and 1.0001. I'm going to put this in as y1. So my equation I'm putting in for y1 is 3 plus 2x plus x squared over 2. And then I'm going to go to my table, and I'm going to put in my t values, which are x for this, y is s. So as far as my calculus is concerned, this is x and this is y1. You just have to know that. That's how your calculator thinks. You can't change your calculator's thinking. So just know that it's portraying the same problem, it's just using different letters to represent it. And we type in all our numbers there. 1, I hope, there we go, 1, 1.1, 1.01, 1.001, and 1.0001. We're getting these results, which are rounded. Make sure we go unrounded, completely unrounded. Do not round at all. Go 55 decimal places, will show you. I can't imagine getting it more than 8 or 9, but just go as many decimal places as you can on each one of these. So for 1, I get 5.5. For 1.1, I'm getting 5.805. Just make sure you're highlighting it up here and look down at the bottom, see what it actually is. 5.53005. And then we get 5.503005. And then we get 5.00300005 for all of our results there. This point is closest to this point. That's the point we care about because we're trying to find the instantaneous velocity when t equals 1. So the slope between these 2 points is going to be much closer to the answer than the slope between these 2 points. Although they'll both be rather close because 1.1 is also pretty close to 1. It's not as close as 0.00 or 1.001 or even 1.0001. So what I'm doing for part A, 1, 2, 3, and 4 is it asks me for the average velocity from 1 to 1.1. This is meters. Change in y is change in meters over change in time is change in seconds. Meters per second is velocity. So if I'm trying to find number 1, average velocity from 1 to 1.1, it's simply going to be the slope between these 2 points. So I take y2 minus y1 divided by x2 minus x1. That gets me 0.305 over 0.1, which is 3.05 meters per second. For number 2, average velocity from 1 to 1.01. So they're concerned about these 2 points. So y2, y1. So the average velocity from 1 to 1.01 is y2 minus y1, 5.53005 minus 5.5 all over 1.01 minus 1. That comes out to 0.03005 divided by 0.01, which is 3.005 meters per second. Number 3, average velocity from 1 to 1.001. From 1 to 1.001. So 3. Average velocity from 1 to 1.001 equals y2 minus y1 all over, I got too many zeros in one of those. 5.53005, 5.030005. This is 5.500300005. There we go. All right. Helps to write down the right number. So continuing on. This has an extra 0 in it. Over 1.001 minus 1. So again, y2 minus y1 over x2 minus x1. If I work it out, subtract 5.5, I end up with 0.0030005 over 0.001. That gives me 3.0005 meters per second. Finally, for number 4, we're going from 1 to 1.0001, so y2 minus y1 over x2 minus x1. So step 4, velocity from 1 to 1.0001 is going to be 5.5003 00005 minus 5.5 all over 1.0001 minus 1. That comes out to 0.00030005 over 0.0001, which ends up being 3.0005 meters per second. That's all part A is. Create your chart, don't round, give me slopes. y2 minus y1 over x2 minus x1. Close, closer, closer, closest. You're going in that order, that direction, looking at these slopes. So, close, closer, closer, closest. To do part B, you just simply ask yourself, where are they going to? And the answer, obviously, hopefully to you, is 3. So the instantaneous velocity is 3 meters per second. That's how you do part B. The answer should be approaching a number. If they aren't approaching a number, you probably rounded your numbers in here. As you found out on the last quiz when you had a problem similar to this, some of you rounded a lot of numbers, and all of a sudden they were approaching something and they went to something else and you didn't know what to do with it. So don't round, get as many decimal places as you can, and the numbers should be very obviously approaching a number. If they aren't, go back to your chart, make sure you don't round, make sure you wrote down all the numbers correctly. Those are the types of mistakes that will happen. As you saw, I even made a mistake myself here. I didn't put enough zeros on there. So be careful writing all the numbers down, that they're written down properly, and all will go well.